Hello everyone, my name is Chris Free and I'm a postdoctoral researcher at the University of California, Santa Barbara, and I'm excited to talk with you today about the future of seafood under climate change. Over the next 15 minutes, I'm going to give an overview of the importance of seafood to human society, the impact that climate change is likely to have on the production of seafood from both wild capture fisheries and aquaculture, and the opportunities for adapting ocean food systems to mitigate these impacts and maintain the ocean as an important source of food through the end of the century. Many of you have tuned into this talk because you're curious about the future for the tuna you eat in your neighborhood sushi restaurant or the future for the farmed salmon that you buy at the supermarket, and you're not the only ones. Wild and farmed seafood are a critically important source of food, nutrition, and income to millions of people around the globe. In 2017, an estimated 59.6 million people were directly engaged in fisheries or aquaculture, and even this large number is likely to underestimate participation in small-scale fisheries like those shown in the bottom panel. Furthermore, over half of the planet depends on seafood for more than 20% of their daily protein intake, and in many island nations, seafood represents over half of daily protein consumption. Finally, seafood provides a rich source of micronutrients such as zinc, iron, and calcium, especially in tropical developing countries suffering from high rates of malnutrition. The demand for animal-based protein and for seafood in particular is only expected to grow as society is becoming increasingly wealthy, diet preferences shift accordingly, and the human population grows toward 9.8 billion people by 2050 and 11.2 billion people by 2100. Although historically the majority of seafood has come from wild fisheries, the majority of future demand will likely be met through aquaculture production. This figure from the United Nations Food and Agricultural Organization shows that while capture production has remained relatively stable since the 1980s, aquaculture production has grown rapidly and now produces almost as much live weight production as wild capture fisheries. Given the importance of marine fisheries and aquaculture to feeding a human population, there's lots of interest in understanding how climate change is likely to impact fisheries and aquaculture and what can be done to mitigate any of the negative impacts. Climate change stands to impact fisheries and aquaculture through a number of mechanisms. On the fisheries side, fish and invertebrates are shifting distributions to track their preferred temperatures. Changing environmental conditions are also altering growth rates, mortality rates, and the rates of juvenile recruitment into the adult population. And the sum of these changes alters overall fisheries productivity. On the aquaculture side, changing environmental conditions can also change where aquaculture is viable. Ocean acidification can threaten the viability of the aquaculture of oysters, clams, and other shell-forming organisms, and harmful algal blooms and storms are expected to increasingly threaten aquaculture operations. In order to prepare for these threats, we need tools for predicting the impacts of climate change on marine ecosystems, as well as tools for adapting food systems to these impacts. On the fisheries side, a really nice paper by Lotz et al. Came out in PNAS last year that ensembles the predictions of 6 different ocean ecosystem models to establish the most authoritative forecast of the anticipated impacts of climate change on ocean fisheries yet. They forecast declines in productivity toward the equator and increases in productivity towards the poles as stocks shift distributions to track their preferred temperatures. In this figure, declines in abundance from 2000 to 2100 are shown in red, whereas increases are shown in blue. This inequity in climate impact worsens with increasing emissions, as seen here, with even deeper reds at the equator and deeper blues at the poles under a business-as-usual emission scenario. When integrating impacts across the global ocean, they forecast a 4% decline in abundance under the least severe emission scenario and a stunning 18% decline in abundance in the most severe emission scenario. This clearly shows the importance of reducing emissions consistent with the Paris Climate Accords if fisheries are to be an important source of food into the future. However, Human responses to these changes could make the impact of these changes on human society better or even worse. For example, a failure to rebuild overfished fisheries and to account for climate change in fisheries management could result in greater losses in catch than expected from climate change alone. On the other hand, the benefits of reforming fisheries management to end overfishing while also accounting for climate change could offset or even outweigh the negative impacts of climate change. In the next few slides, I'm going to walk through the reforms necessary to prepare fisheries for climate change and then show the potential benefits of these efforts. First, ending overfishing and rebuilding overfished fish populations will go a long way towards both enhancing the ecological resilience of fish populations to climate change and to increasing long-term yields from fisheries under climate change. The FAO estimates that 33% of global fish stocks are currently overfished and therefore currently producing less catch than would be possible if they were fished at sustainable levels. An additional 8% are currently underfished, and expanded fisheries for these underutilized resources could also contribute to increasing long-term yields. Efforts to sustainably manage fisheries will have to be context-specific. In places like the US, with high scientific and management capacity, this might come from the development of new tools for forecasting shifts in distribution and productivity, or from developing regulations that are robust to changing environmental conditions. In places with lower scientific and management capacity, establish or strengthening access-based management that aligns economic conservation incentives could pave the way towards more sustainable management. Second, fisheries management will have to account for climate-driven shifts in productivity and distribution through high degrees of regional or international cooperation. This animation shows the forecast shift in the distribution of Peruvian anchoveta, the world's largest fishery in terms of catch volume, and illustrates the international scale of these two challenges. Here, we see two things happening. First, we see the distribution of Peruvian anchoveta is expected to shift poleward out of Peru and into Chile. Without international cooperation, what is to incentivize Peru not to fish out Peruvian anchoveta before it exits its waters? Second, we see that the size of the Peruvian anchoveta distribution is shrinking, which likely means that the productivity of anchoveta is also shrinking. Detecting and responding to this shift will be impossible without international cooperation that promotes data sharing and establishes clear rules for allocating catch limits in response to both these shifts in productivity and these shifts in distribution. In a recent paper with my UCSB colleagues, we examined the extent to which the benefits of such fisheries management reforms could offset or even outweigh the negative impacts of climate change. To do this, we forecast shifts in the distribution and productivity of about 700 harvested seafood species around the world and estimated the amount of catch that could be derived from these species in scenarios with and without climate-adaptive fisheries management reforms. Even with emissions reductions consistent with the Paris Climate Accords, a failure to reform fisheries management would result in lower catch in 2100 relative to today in most tropical and temperate latitude countries. However, with fisheries reforms that end overfishing while accounting for climate change, the majority of countries could see increases in catch into the future. However, the potential for fisheries reforms to offset the negative impacts of climate change depends strongly on our efforts to reduce greenhouse gas emissions. Under a so-called business as usual emissions scenario, outcomes under business as usual fisheries management are far worse than under the aggressive emissions reduction scenario. And reforms are not able to offset these negative impacts in many tropical countries. In countries where fisheries reforms will be insufficient for increasing catch under climate change, or where increasing catch is insufficient to meet rising food demands, we will need to look to other food sectors to complement the gains from fisheries management reforms. Offshore marine aquaculture is a promising candidate, and in this next section I'm going to walk through the reforms necessary to increase mariculture production under climate change and results from our work describing the potential benefits of these reforms. The first pathway to expanding mariculture under climate change will be to establish policies that promote sustainable mariculture development. In many highly regulated countries, such as the United States, mariculture development has been slow due to complex and overly precautionary regulations. In these countries, the process for permitting sustainable mariculture operations need to be streamlined to foster sustainable growth. In countries with more relaxed environmental regulations, such as China, mariculture has grown unsustainably, leading to enormous environmental impacts and ultimately to mariculture collapse. In these countries, stricter guidelines on mariculture best practices will be necessary to ensure sustainable development. The second pathway to expanding mariculture under climate change will be to invest in technological innovations that increase the efficiency with which mariculture species can be grown, or to increase the tolerance of mariculture species to changing environmental conditions. Currently, feed for finfish mariculture depends on ingredients derived from wild captured fisheries. This means that the availability of feed ingredients from capture fisheries places a limit on the production potential for finfish mariculture. Thus, developing new ingredients and technologies for replacing wild fish ingredients would greatly expand the potential for finfish mariculture. Fortunately, this is already happening very rapidly within the industry. Furthermore, while selective breeding of livestock for fast growth or other favorable traits is the norm, selective breeding of mariculture species for fast growth has been rare. Only 10% of mariculture species are currently bred for fast growth, and evidence suggests that breeding a larger portion for fast growth would more than offset the negative impacts of climate change. Finally, mariculture species could be bred for increased environmental tolerance, so as to allow them to be grown in even the fastest warming or fastest changing waters of the ocean. The third pathway to expanding mariculture under climate change is to promote access to financial resources such as credit and insurance. Climate change is expected to increase environmental variability and the frequency and intensity of storms and harmful algal blooms, which collectively threaten mariculture infrastructure and operations. Increased access to credit and insurance would provide buffers against these uncertainties and help promote mariculture expansion. The fourth and final pathway to expanding mariculture under climate change is to use marine spatial planning tools to locate mariculture operations in areas of low risk and areas that present minimal potential impacts in other sectors, such as fisheries or tourism. Furthermore, mariculture may even be positioned to enhance ecosystem services. For example, the farming of filter feeding bivalves may be used to reduce eutrophication and harmful algal bloom risk, and the farming of nutrient-absorbing seaweeds could help prevent eutrophication and blooms before they even happen. I am currently working with a large team of colleagues to understand the potential for these reforms to expand mariculture production under climate change. In short, we collected information on the environmental tolerances of 200 mariculture species from around the world and mapped suitable sites for mariculture through 2100 under various climate change scenarios. We also collected information on the costs of conducting mariculture and removed sites where mariculture would be unprofitable or where there are already existing ocean uses, such as marine protected areas or shipping lanes. For finfish mariculture, we estimated the availability of feed from the capture fisheries scenarios that I described earlier and used this availability to limit the potential for growth in the finfish mariculture sector. We found that even under business as usual emissions, bivalve and finfish mariculture will be possible in high volumes in nearly every country around the world. To this point in the presentation, we've reviewed the predicted impacts of climate change on marine fisheries and the aquaculture, as well as the potential for adaptation to mitigate many of these negative impacts. With this information, we can now ask where adaptive actions might be able to increase the production of seafood in the future, and where international trade or terrestrial food production will have to fill in losses of food from the ocean. With emissions reductions consistent with the Paris Climate Accords and climate adaptive reforms in fisheries and aquaculture, all of the countries shown in blue could increase the production of seafood from both sectors into the future. These countries shown in the countries shown in green would lose production from ocean fisheries, but it could offset these losses with gains from mariculture. Only the countries shown in red would see losses in net ocean seafood under climate change. However, without dramatic emissions reductions, even the best reforms in fisheries and aquaculture will be insufficient to offset the negative impacts of climate change. In this map, you see many more countries in red, indicating net losses in seafood production, and fewer countries in green, where aquaculture production could offset fisheries losses. I want to conclude by saying that this presentation was intended to be hopeful. It was intended to show that swift and effective adaptive actions could mitigate many of the negative effects of climate change. However, I want to highlight that first and foremost, achieving these benefits will require reducing emissions consistent with the Paris Climate Accords. The effectiveness of the reforms described here deteriorate rapidly under increasingly severe climate scenarios. Finally, I also want to highlight that even in the best case scenario, where some countries will still suffer losses in domestic seafood production, filling in these gaps will require advancements in other food sectors, which may themselves be suffering losses from climate change. I hope that we will have the opportunity to discuss this and other challenges in the panel discussion. Thanks so much for your attention, and I hope to see you in the panel discussion later this week.